The light that we see is a type of electromagnetic radiation. Electromagnetic radiation carries energy through space in several different forms, which we'll take a look at now. This diagram represents the electromagnetic spectrum. The visible part of the spectrum, the light that we can see, is actually a very small slice of the entire spectrum. So let's take a look at the parts of the spectrum that we can't see, starting with radio waves. Radio waves bring music to radios, but they also provide signals to cell phones and TVs. And radio waves are really big. Look at the wavelength of a radio wave in the range of 10 to the third meters. A radio wave could actually be the size of a football stadium. Slightly shorter in length but higher in energy are microwaves. And where radio waves might be 1,000 meters, 10 to the third meters or 1,000 meters, microwaves are shorter, maybe in the centimeters range, and a lot higher in energy. And so they can penetrate rain, snow, clouds, and smoke, making them really useful to view Earth from space, which helps us to determine moisture patterns, among other things. And even shorter in length and higher in energy are infrared waves. Now, infrared waves in terms of wavelength are going to be 10 to the negative fifth meters, or less than a millimeter. Many things, including humans, give off infrared light. And that's how some types of night vision goggles work. We have somebody that's wearing camouflage here, but looking at him here, he's emitting infrared radiation or infrared light that's able to be picked up by certain types of night vision goggles. The infrared range is actually kind of a long range. We have at this end called far infrared, which is closer to the microwave end. So they're longer, maybe about the size of a pinhead, and they're thermal in the form of heat. Then closer to the visible part of the spectrum, we have near infrared, which is closer to visible light, and these wavelengths are microscopic, like maybe the size of cells, and they can't be felt. They're not thermal. Which brings us to the only part of the spectrum that we humans can see, the visible section. Now, these waves have a range of colors starting at the low end of the spectrum with red, and moving up to the higher end of the spectrum with violet. Red, being a lower energy color light, is a light that's often used in dark rooms when printing photographs onto paper. Because it is such a low energy light, it's called a safe light, and it's not going to expose the paper in the developing process. And then at the other end of the spectrum, we have black light, which really, in truth, is closer to the UV end of the spectrum. And black light, being closer to violet in color, is going to be a really high energy color wavelength of light, which is why it can make some substances appear to be glowing. And in terms of wavelength, visible light is going to be around 10 to the negative sixth meters, which puts it around close to a millionth of a meter. So notice now, as these wavelengths are getting shorter and shorter and shorter as we move across the spectrum, this is getting closer and closer together. These wavelengths are getting closer and closer together. And so as these wavelengths get shorter, the frequency that they're moving at is getting greater and greater. And so now we're moving up into the ultraviolet range of the electromagnetic spectrum, and really short wavelengths and high frequencies. Stars and planets give off UV light, and the sun provides us with a steady supply, which is why we take precautions to avoid it in using sunscreen and sunglasses. which is also the reason why, since we're getting into very high energy waves here, they can be damaging to your skin. And so tanning beds are a no-no. Next we have X-rays. Again, getting shorter and shorter in terms of wavelength and higher in terms of frequency or energy. And we're getting into the range of the spectrum where the wavelengths are so short and so high in energy that they begin to act more like particles than waves. And that's going to be addressed in a separate video. And so X-rays are also emitted by the sun and black holes and things in space. And since bones and teeth, which are rich in calcium, are dense, they absorb more X-rays than skin does, making them look white on X-ray film. And finally, we have gamma rays. These are the smallest wavelength, highest energy radiation. It comes from nuclear explosions in space. These are such high energy waves that they can kill living cells. And in fact, we do use them in medicine to kill cancer cells. This is called a gamma knife. And gamma rays are pinpointed at a particular tumor or growth to kill the cells in that area. So we started with big waves, the size of a city block, to waves that are really, really, really tiny, those gamma rays. And I said they have really high energy. So let's take a look at how this all gets put together. Waves result from energy coming from someplace, like for example a boat. And if you've ever been on the water and gotten caught in the wake of a bigger boat, you know you get bounced around in an up and down motion. Here we'll look at the relationship between frequency and wavelength. Starting with wavelength, whose symbol is lambda, and see it even kind of looks like a wave. If you look really, really closely up there, you can see a little guy surfing on the top of that wave. Look, you see him? So wavelength then is the distance from peak to peak of two adjacent peaks. Or wavelength could be measured from trough, the low point in the wave, to trough of two adjacent waves. And as I've mentioned, wavelength is measured in meters. The number of wave cycles to pass a given point, say from here to here, each second is the frequency. The symbol for frequency is a nu that actually looks more like a V. And the units are in hertz or cycles per second. So you can see that the relationship here between frequency and wavelength is the shorter the wavelength, the shorter the distance from peak to peak to peak, the higher the frequency, the more times those waves are going to pass through a given point in time, compared to a longer wavelength from peak to peak in a certain amount of time is going to have a lower frequency. That wave is going to pass through those 2 points in time much slower. We know that all electromagnetic radiation moves through a vacuum at a rate of 3.00 times 10 to the 8th meters per second, which is the speed of light noted by the symbol c. And as I stated earlier, when we go back to look at our spectrum, the longer the wavelength, the lower the frequency, the shorter the wavelength, the greater the frequency. And so mathematically, that relationship is the speed of light, c, is equal to its wavelength times frequency. The speed of light, or electromagnetic radiation, is a constant. It never changes, which means if we increase wavelength, that the frequency is going to decrease proportionally, and vice versa. This kind of a relationship is known as an inverse relationship. As one variable increases, the other decreases proportionally. And this concludes this portion of the electronic structure of the atom.